Greetings once again. Welcome to my YouTube channel for Kangaroo Maths and Science Academy. Together we strive for a change through education. Ladies and gentlemen, I want to take you through part 2 for Physical Science paper 2 on tips on how to ace Physical Science exam with good marks. And ladies and gentlemen, here is my YouTube channel ID. If this is your first time, kindly just to make a good follow-up, just watch my first video that I just done for the tips to ace Physical Science paper 2. There's a link that I've shared below. Kindly follow it. Don't forget to like, subscribe. And ladies and gentlemen, in part 1, I went through organic chemistry, where I looked on like nomenclature, but I did not address it much because there is a video that I created for nomenclature and the physical properties and the chemical properties of organic compounds together with the organic reaction. This one, I've already covered it in part 1. So kindly follow the first video in order to understand organic chemistry. Right, ladies and gentlemen, now we're going to move on to chemical change and the rate of reaction. Right, under chemical change, you need to be able to define what is endothermic reaction and exothermic reaction. So it's very important for you to be able to define the term endothermic and exothermic. And also you need to be able to define the term, the heat of reaction, or in other words, they call it a change in enthalpy, change in enthalpy. So you need to be able to define the term heat of reaction or changes in enthalpy. Again, you need to be able to define what is an activation energy and an activated complex. Also, you need to be able to draw a potential energy graphs for endothermic and exothermic reaction. Then again, lastly, you need to be able to define what is a positive catalyst. It's very important. Actually, this is grade 11 work, but it's also being asked in grade 12. This is grade 11 work, but you need to make sure that you know this, right? Again, now let's start with the chemical change. First of all, I'll define what is endothermic and what is exothermic reaction. So it's very important to be able to know this definition, right? What do you mean by an endothermic reaction? Endothermic reaction is a reaction in which energy is absorbed. A reaction in which the energy is absorbed or is taken in, that is called the endothermic reaction. Whereas exothermic reaction is a reaction in which energy is released. It's released or liberated. So the reaction in which energy is released or liberated is called the exothermic reaction. So it's very important, ladies and gentlemen, to differentiate between the term endothermic and exothermic, because when you're going to talk about chemical equilibrium, someone will be using these terminologies. So make sure that you understand this. And again, you need to be able to define what is the heat of reaction or what is the change in enthalpy. Right. A heat of reaction, it is the total energy absorbed or released in a chemical reaction. Total energy absorbed or released in a chemical energy. It's in a chemical reaction, it's called the heat of reaction. So total energy absorbed, either absorbed or released in a chemical reaction. Now, this delta H, or the change in enthalpy, there is a formula for calculating the heat of reaction, which is calculated by taking the energy of the products minus the energy of the reactants. So energy of product minus the energy of the reactants, that is called the heat of reaction. And ladies and gentlemen, wherever we have an endothermic reaction, the heat of reaction is always bigger than 0. What does this mean? It means that the energy of products are greater than the energy of the reactants. So which means there are more products in terms of energies, more products than the reactants. So it means if you want to check that you are dealing with the endothermic reaction, the heat of reaction should always be bigger than 0, which means there is more energy of products than the reactants. However, for an exothermic reaction, heat of reaction is less than 0, which means we have more reactants, or the energy of the reactants, more reactants than products. Or energy of product is less than the energy of the reactants. That's why the answer becomes negative. So it's very important for a learner to be able to consider or to look at these signs, especially in the reaction. We'll talk about this when we are going to deal with chemical equilibrium, ladies and gentlemen. So these are the things that a learner should be able to understand in order to get good marks in physics paper 2. Again, we have what you call the activation energy and the activated complex. And this activation energy, we also spoke about it under the rate of friction, where we talk about when we're explaining collision theory in terms of the addition of a catalyst. Right, you need, or a learner need to be able to define what is an activation energy, the EA. So these are some of the terminologies that you need to be able to know. Number one, an activation energy is the minimum energy that is needed for the reaction to start or to begin or to initiate. So the minimum amount of energy needed or required for the reaction to start or to begin. So that amount of energy, or that minimum amount of energy that is needed for the reaction or for the chemical reaction to start, that is called an activation energy. So these are the terminologies that a learner should be able to understand when we're dealing with chemical change. Then another one is the issue of being able to define what is an activated complex. Activated complex is the transition from the reactants to the product in a chemical reaction. Actually, the unstable, let me just say unstable, the unstable, I apologize, unstable transition. Why are we saying it is an unstable? Because it can change at any time. So it is an unstable transitions from the reactants to the product in a chemical reaction. So this is called an activated complex. So a learner should be able to define this, ladies and gentlemen, understand, not claim it, but understand, and it will be easier for a learner to answer the questions in the exam. Then the other one, you need to be able to draw the potential energy graphs for both endothermic and exothermic reaction. I think I'll explain this. Then again, you need to be able to define what is a catalyst or what is a positive catalyst. The reason we say a positive catalyst means we still have catalysts that can act as inhibitors. That's why we just want you to define the term positive catalyst, not just a catalyst. All right, let's now define what is a catalyst, ladies, a positive catalyst. All right, a catalyst or a positive catalyst is a substance that speed up the chemical reaction. A substance that speed up the chemical reaction by lowering or by reducing the activation energy without undergoing any permanent change. What does this mean? Permanent change. So I want to explain this so that you can understand. The function of a catalyst in a chemical reaction is to speed up the reaction by lowering or by reducing the activation energy, however, without undergoing any permanent change. What does this mean? It means, yes, it is lowering the activation energy, but it does not change the reactants and the products. So if we were to talk about in the context of chemical equilibrium, when we're going to talk about the Letallia's principle, you'll realize that a catalyst has no effect on chemical equilibrium. Why? Because it does not change the product or the reactants. It is there to speed up the reaction, either for a forward or for a reverse. So actually increase both the forward and the reverse. So it means it will not affect chemical equilibrium. But however, we'll talk about that when we're going to talk about chemical equilibrium, ladies and gentlemen. So it's very important for a learner to be able to understand this, not just for learning, but understanding, ladies and gentlemen. Right. Let's now go through the issue of graphs, ladies and gentlemen. A learner must be able to make interpretation of the potential energy graphs in terms of endothermic and exothermic reactions. Right. Let's now talk about the potential energy graph for endothermic. Remember we said where we have endothermic reaction, delta H should be bigger than 0. But this one, the delta H should be less than 0. So it means when we draw this, let's say we construct our potential energy graph. Okay. Okay, so I'll take this as the y-axis, and this is the x-axis. So this is called potential energy. This is the part for potential energy. For now, we can just say it is in kilojoules. And this side, this will be the cause of reaction. This will be the cause of reaction. Then now, when the reaction starts, usually, it starts with reactants. Then now, these reactants, I'll just call them the R, they need a specific energy for the reaction to start, which is called activation energy. So it means the activation energy will be provided to the reaction then up until it reaches a activated complex, and the products are formed. Here is the product. Now, ladies and gentlemen, I want us to talk about this so that you can be able to understand. This is called the potential energy graphs, but for endothermic. I'll explain to you why I was saying it's endothermic reaction. If you look at these potential energy graphs, this is the energy of the reactants here. Then along here, somewhere here, this is the energy of the products. So you can easily see that the energy of the products, it's now, the energy of the product, it's now bigger than the energy of the reactants. So which means this is endothermic reaction. Then, okay, fine. Since we have our graph there, we need to talk about something called the activation energy and activated complex. From the reactants, the unstable, let me just talk about this point first. You see this point here, the maximum point of this potential energy graph, this point, is the one that is called an activated complex. Why it is called an unstable? It means it can come down, can increase, can decrease. So but it's a transition from the reactants to the product. Now, I want you guys to listen to me very well. From the reactants, let me just try to visualize this. From the reactants to the activated complex, from the reactants to the activated complex, just from here up until there. This is called an EA, it's called an activation energy. Let me just write it this side. So from here up until here, this is called an activation energy. But this activation energy, it is an activation energy for a forward reaction. So if they say, calculate the activation energy for the forward direction, they're just referring to from the reactants to the activated complex. But from the activated complex to the product, this one is still an activation energy. It's still an activation energy from the product to the reactants. From the product to the activator, so this is still an EA, but this one is for a reverse. So we have an activation energy for a reverse, we have an activation energy for a forward. Then just between the reactants, this gap here, it's where we call it the activation, the heat of reaction, I mean to say, which is energy of product minus energy of the reactants. But if we add a catalyst, ladies and gentlemen, let's say we add a catalyst. Addition of a catalyst means we will not change the reactants. It will just reduce the activation energy. So the first one is the uncatalyzed one. This one is so you can easily see that the activation energy has been lowered because from the reactants to the activated complex, this is our activation energy, which is smaller than the original one. So this one is for a catalyzed one. So you can easily see that for a catalyst, it is a substance that speeds up the reaction by lowering the activation energy without undergoing any permanent change. It means without changing the reactants or the products. So it's very important to be able to know that. So you need to be able to analyze a potential energy graphs. And again, ladies and gentlemen, it means for an exo, it's a different case. For an exo, it means you have something like this. Product are now less than the reactants. So it means we have more reactants than product. The energy of the product, it's less than the energy of the reactants. It's below actually. So this is an example of an exo, because this one is an endothermic energy, potential energy. So this one is for an exo. And they usually ask this guy questions in a multiple choice in a multiple choice format. So you need to be able to understand. Right? If you can look in the context of exo, this is our activated complex. From the reactants to the activated, this is our EA. So the EA for a forward, you see that it's now smaller. But on the endo, the forward activation energy was higher than that of the reverse. But now look at the reverse one. The reverse one is now the one which is higher. Then the difference between this energy, that's why we have the H. So it's very important to be able to differentiate between exo and endothermic reaction in terms of graphs. And these are exam typical questions, ladies and gentlemen. So you need to be able to understand the difference between potential energy for the graphs for endothermic and exothermic reaction. I apologize. Then now, let's now move on, ladies and gentlemen. Now we went through the issue of potential energy graphs. Then I want us to go through the rate of reaction. Ladies and gentlemen, honestly speaking, I've created a video where I spoke about the rate of reaction. What is the rate of reaction? What are the factors that are affecting rate of reaction? The method of measuring rate of reaction, how to calculate average rate of reaction, how to explain the factors that are affecting using collision theory, how to use the Maxwell distribution curve in explaining the factors that are affecting the rate of reaction. Ladies and gentlemen, for now, I will not address this. Kindly watch the video. There's a link that I shared below. Kindly go through it in order for you to understand the rate of reaction. I strongly believe that once you watch this video, your life will never be the same again. You're going to enjoy rate of reaction. Remember, rate of reaction, factors that are affecting rate of reaction are 6. Number 1, it is the nature of the reacting substance. Number 2, it is the concentrations of the reactants. 3 is the temperature. 4, it is the pressure in gases. 5, it is the surface area or the state of division. 6 is the catalyst. So these are the 6 factors that can affect the rate of reaction. Kindly follow the video that I have created for the rate of reaction. I strongly believe you'll enjoy the session. Right, ladies and gentlemen, we can now proceed to chemical equilibrium. Remember, you need to study, you need to go through the video, understand everything that I just explained here. Then you are going to enjoy, you'll enjoy physical science paper 2. Remember, in the exam, there are already 3 marks just for you to define, to apply the principles, making definition, applying principles. Those are just 3 marks. And remember, organic chemistry is one of the topics that has a lot of marks. So you need to make sure that you spend more time on organic chemistry because it will come in 3 questions, as I said. Then again, another one is the electrochemical reactions or electrochemistry that speak of the galvanic and electrolytic cells. So you need to make sure that you understand that. Very important, guys, very important. Remember, a wise man once said, in order to change your life, in order to change your life, you need to change yourself. And by changing yourself, you need to change your mindset. Very important, ladies and gentlemen. Okay, guys, just a okay. Let's now go through the chemical equilibrium. Right, number 1, under chemical equilibrium, ladies and gentlemen, you need to be able to define what is a dynamic chemical equilibrium. Very important, very, very, very important. You need to be able to define what is a dynamic chemical equilibrium. A dynamic chemical equilibrium is a stage in a closed system, where, in which the, or let me say at which, but it's fine, in which the forward and the reverse reaction are equal. So a dynamic chemical equilibrium, ladies and gentlemen, it is a stage in a closed system where or in which the forward and the reverse reaction are equal. So it means in chemical equilibrium, we are talking about reactions that are actually reversible. Right? What do you mean by a reversible reaction? A reversible reaction is the reaction in which product can be converted back to the reactants. The reaction in which product are converted, let me just say, product are converted back to the reactants. A reaction in which the products are converted, in which products are converted back to the reactants. So what does this mean? It means when we are dealing with chemical equilibrium, we're dealing with a reaction where the reactants can form the products and the product can form the reactants. So this double arrow here, it represents that we're dealing with a reversible reaction. So you need to be able to understand or to define what is a dynamic chemical equilibrium and what is a reversible reaction. And also you need to be able to know what is a closed system. Very important, ladies and gentlemen. Then next, you need to be able to know the factors that are affecting chemical equilibrium. Let me say this. Within those 6 factors that are affecting the rate of reaction, which I just said now, the nature of the reactants, the concentration, the temperature, the pressure, the surface area, and the catalyst. It's only 3 factors among those which can affect chemical equilibrium. And factors that can affect chemical equilibrium, there are 3. Number 1, it's concentration. Number 2, it's temperature. Number 3, it is the pressure in gases. So these are the 3 factors that can affect chemical equilibrium. So you need to be able to know the factors that can affect chemical equilibrium. And also you need to state Le Chatelier's principle in words. Which states that, according to Le Chatelier's principle, it states that when chemical equilibrium is disturbed means the forward and the reverse are no longer the same. When chemical equilibrium is disturbed in a closed system, the system will reinstate a new chemical equilibrium, or will reinstate a new equilibrium or chemical equilibrium by favoring the reaction, that oppose the disturbance. So you need to be able to state Le Chatelier's principle in words, ladies and gentlemen, which states that when chemical equilibrium is disturbed in a closed system, the system will reinstate a new chemical equilibrium by favoring the reaction that opposes the disturbances. It's very, very important. Ladies and gentlemen, let me be honest with you. You know, topics like rate of fractions, chemical equilibrium, these are one of the easiest of them all, ladies and gentlemen. Because with this one, you just have to be able to know the definition, know the factors, be able to explain Chatelain's principle, explain it in like the principles in explain the factors that are affecting chemical equilibrium, be able to calculate equilibrium constant, which is the Kc, and also know the factors that can change equilibrium constant, also be able to make interpretations in the graphs. Usually there is an equation where you calculate Kc. On average, usually it's around 8 marks, 9 marks. This one you need to make sure that you spend more time on this. I think I can do an example, but I can also create a video where I'm just going to explain the calculation in terms of the Kc, ladies and gentlemen. And you can also be able to calculate this Kc from the graph. It's very important, ladies and gentlemen. Right, let's move on to the next bullet. Right, in the next bullet it says you need to use Le Chatelier's principles in explaining the factors that are affecting chemical equilibrium. You need to be able to know this. Right. So now I need to explain something very important here. Now, before, okay, let me just you explain the factors in terms of Le Chatelier's principles. Okay, let me just do this. Let me do this first. We know there are 3 factors that can affect chemical equilibrium. Number 1, it's concentration. Number 2, temperature. Number 3, it's pressure. But now, before I talk about the concentration, let's talk about the pressure first. I apologize, guys. According to the Chatelier's principle, it says if there is an increase in pressure, I'm saying in temperature, an increase in temperature will always favor, an increase in temperature. You must know this. When you increase temperature according to the Chatelier's principle, you always favor endothermic reaction. An increase in temperature favor endothermic reaction all the time, according to Le Chatelier's principle. So you need to know this. So when there is an increase in temperature, always the reaction will favor the endothermic reaction. Okay, then again, number 2, when there is a decrease in temperature, a decrease in temperature favor exothermic reaction, according to Le Chatelier's principle. So this is the first thing that you must write when you are asked to use Le Chatelier's principle. When there is an increase in temperature, you must always favor endo. Decrease, you favor exo. Very important. That is according to Le Chatelier's principles. So in a reaction, you need to be able to know which one of these reaction is endo and which one is the exo. For example, I'm still talking about the temperature. Let's say you are given the following. They give you a reactant, and this reactant forms product, but they write something like this. Oh, okay, let me just make it double arrow. So this double arrow, it means, listen to me very well. If we move from reactants to product, this is called a forward reaction. But if we move from product to reactants, then this is called a reverse reaction. So listen to me very well. In a reaction, if you are given this symbol in a reaction, you must know that this symbol means that the forward reaction is the one which is endothermic. The reverse reaction is the one which is the exothermic reaction. So in the exam, you must be able to look at this. If they give you this, you must know, okay, it means this reaction, it's endo, particularly for the forward. Moving from reactants to product, this is an endo. So it means if the forward is the endo, it means the reverse will be the exo. Again, they can write the reaction like this. You have the reactants, and now they form a product. But here they write something like this, delta H. Then they write a positive value. They give you a value, but this value is actually positive. Same applies. Same applies. It means this reaction actually is endothermic, particularly looking at the forward. It means the forward is the one which is endo. The reverse is the one which is exo. Sometimes, number 3, sometimes they can do it like this. It might be the reactants that forms product plus the energy on the product side. What does this mean? It means the product has absorbed more energy than the reactants. And also, this is an example of an endothermic reaction. So it means the forward is the endo, and the reverse is the one which is the exo. But if we have something like this, ladies and gentlemen, reactants forming the product, but delta H, it's less than 0. Or reactants forming the product, but the delta H, it's a negative value. Or the reactants plus the energy produces the product. You must be careful. You see, the energy are now on the left. So it means it shows that the reactants has more energy than product. So this is an example of an exothermic reaction. Particularly for a forward. Which means if you have this, it means that the forward reaction is the one that is exo. Then the reverse is the one that is endo. Same applies. This value, forward it's exo, reverse it's endo. Same applies. This value, forward it's exo, reverse it's endo. I believe you are following, ladies and gentlemen. So you need to make sure that you check this very well when you're given a question paper. Okay, right. Then now, the other one, remember I said if you want to explain the Chatelier's principle in terms of temperature, you need to look at these keywords. Increased temperature, always favor endo. Decrease favor end temperature, always favor exo. So now, when we say a reaction is favored, I think we need to talk about this very well. Where the reaction is favored means the end result of that reaction will the concentration will be higher than the what it was before. But we'll talk about that, ladies and gentlemen. Right. Another one very important before I talk about concentration is the issue of pressure. Pressure in gases. By the way, guys, this is very important. In a reaction, you only speak of pressure when your reactants are in gas phase. We need to consider, you talk about pressure if you're dealing with substances that are in gas phase. Gas phase, not aqueous, not solid. No. Right. In terms of pressure, according to Boyle's law, it says pressure, it's inversely proportional to volume. So what does this mean? An increase in pressure, decrease volume. A decrease in pressure, increases volume. However, the number of moles and the volume are directly proportional. So what does this mean? It means, listen to me very well. According to Le Chatelier's principle, an increase in pressure which is a decrease in volume actually. An increase in pressure, which is the same as decrease in volume. An increase in pressure, ladies and gentlemen, always favor, favors the reaction with fewer or less number of moles. Why? Why this? Why this? Let me explain it so that you can understand. Remember, we say when you are increasing pressure, according to Boyle, increasing pressure result to a decrease in volume. But in Boyle's law, like the assumption is that the temperature should remain the same. So an increase in pressure result to a decrease in volume. And ask yourself, if there is a decrease in volume, because I said number of mole and volume are directly proportional. I'm saying if there is a decrease in volume, it means even the number of mole will still decrease. That's why here we say an increase in pressure, according to Chatelier's principle, always it favored the reaction with fewer or with less number of moles. So increasing pressure, you must favor the side that has fewer number of moles. But a decrease in pressure, which is the same as an increase in volume, the reaction will favor the reaction with more number of moles. Why this? Explaining it again. If pressure is low, volume becomes higher. And if volume becomes higher, number of moles has to be more. That's why a decrease in pressure, according to Le Chatelier's principle, it must favor the side that's the reaction with more number of moles. This is according to Le Chatelier's principle. So in the exam, you need to be able to, it's okay, increase pressure, favor the side that has fewer number of moles. Decrease pressure, favor the side that has more number of moles. Very, very important. Now, something good about concentration. I want to explain this because I was supposed to start with it, but I want to make it the last. In terms of concentration, here is my scenario, ladies and gentlemen. Increasing in concentration. Let's say of substance A, or actually saying adding more of A, the same as when you say adding more of A. Let me explain this so that you can understand, guys, especially in the context of, but with this one, you're fine. Let me explain this so that you must not forget. Ladies and gentlemen, increasing the concentration or adding more of a substance in a reaction does not mean that that thing will actually increase at the end. Let me explain to you why I'm saying this. Here it is the end result. Let's talk about the context of, let me just give you a simple scenario. I strongly believe that most of you knows there is this juice called Oros. I apologize, but let me talk about this. When you buy it from the shop, ladies and gentlemen, it's already written that it is highly concentrated. What does this mean? Now I'm taking you back to acid and base. It shows that in terms of its concentration, it has more number of moles in proportion to the volume of water. Now, look at this, ladies and gentlemen. If, let's say, you take this Oros, maybe you put it inside a cup, maybe let's say just a small of it. Then you take a sip. What will happen? This sip, it will be highly concentrated actually. Let's just be honest, without adding any water. It will be very sweet, just sweeter actually. So now, it means that for you to consume it, what must you do, ladies and gentlemen? You have to add water to dilute it. But now, ask yourself, do you see that the addition, remember inside it's juice, is that juice? So which means if you keep on adding water, water will use more of the juice. The water content will use more of this juice. Which means, so as a result, what's going to happen? If it uses more of this sweetness, what's going to happen? It means the concentration of the juice will decrease. It will no longer be sweeter like before. And as an end result, it means even though the concentration of water will also get reduced because it has been used mixed up with juice, then you're going to form something. You're going to form a mixture whereby it will be more of this. So you can easily see that here we added more of water, but this water has used more of this. And as a result, if it uses more of this, means this will end up decreasing in concentration. So what does this mean? It means when you are dealing with concentration or, yes, addition of a substance, yes, there is something that you need to understand here. Let me explain it thoroughly so that you can understand. Ladies and gentlemen, this was just an example. This was just an example. Let's say we have two substances. Just want to explain in the context of concentration. So if let's say you have, let's say here are the reactants. So we have A, let's assume it's an aqua. It reacts with B, it's also an aqua. Then it must form, okay, let's assume the reaction is reversible. It must form, let's say, AB, just something different. Now, look at this. If we say we want to increase the concentration of A, I'm referring to this, is the same as we say we're adding more of A. Adding more of A is the same as when we say we're increasing the concentration of A. Look what is going to happen. I want to explain it so that you can understand. I'll say, by adding more of A, the same as increasing the concentration of A. By adding more of A will use more of B, which is true. Most remember, A is reacting with B. So if we add more of A, then this A will end up using more of the B. It will use more of this B. And as a result, what's going to happen? The concentration of the B will decrease. Just true. And also, the one we just added, because it's reacting with B, also even its concentration also will be reduced, will decrease too. So it means even the concentration of the A now will decrease because it has reacted with B now. And what? Which means that because we are taking this, reacting with this in order to form this. If this one we have added more of A, it will use more of the B. And once it uses more of the B will decrease in terms of concentration. And as a result, even that A that we have added will end up decreasing. But it will form more of the B. So it means of the AB. So it means as a result, concentration of AB will increase. So it means by adding more of this will use more of B. B will end up decreasing in concentration. Even the A will also increase. So as a result, it means we're going to have more of the AB. So you see that once we have a decrease in one side and we have an increase in other side, it shows that one side is being favored. So it means a forward reaction. A forward reaction is favored. Why? Because it's the side where there is an increase. So this side, it has decreased, and this side, it has increased, which means a forward reaction is favored. So what does it mean? It means increasing the concentration or adding more of a substance in a reaction does not mean that substance is going to increase. It's actually going to decrease, according to literature. Because if we add more of A, the A will eventually use more of the B. And what's going to happen? Concentration of the B will decrease. And also, if the concentration of the A will also decrease. So as a result, it means AB will end up increasing. And it means a forward reaction will be favored. So it means the opposite would be now the same. Adding less or removing more of A will use less of the B. So which will be the opposite case. So you need to be able to understand this, ladies and gentlemen. I believe you are following. I believe you are following. So I will do an example relating to these 3 factors. In terms of concentration, pressure, you only speak of gases. For example, let me do this. I'll just write down a hypothetical reaction just to address some of the things which has to do with chemical equilibrium. Number 1, let's look at this. Let's say we have the reaction like substance, it's A, it's an aqua. B, it's a gas. Okay, let's find. Let's just say we have, yeah, just an example, it's fine. The reaction is reversible. And this time around we have C, it's a gas, and D, it's an aqua. It's just an example. The mole ratio here we have 2. Here we have 3. There we have 1. There we have, let's say, 1 also. Just an example. And here they write this, delta H bigger than 0. Then the exam says, the question says, what will happen to the concentration of C, just an example, if, number 1, temperature is increased. I want you to temperature is increased. You only write down increase, decrease, or remains the same. Secondly, pressure in gases or pressure is increased. Number 3, catalyst is added. Number 4, concentration of A increased, or they've added more of A, still the same. Yeah, just an example. Number 1, we need to first look at our reaction. In our reaction, the reaction is reversible. The reaction is reversible. Then we also have this guideline. We know if the delta H is bigger than 0, it means this reaction is endo. But which endo? Endo for a forward, because this is a forward. So it means the forward is the endo. The reverse is the one which is the exo. So now, number 1, we need to explain the first one. It says, what will happen to the concentration of C? We're interested in C. I need to know whether the C will increase, decrease, or remains the same. That's what we want. So you either talk about increase, decrease, or remain the same, or no effect. Right, let's do this. Listen, fine, we'll start with temperature. Number 1, we know that according to Le Chatelier's principle, an increase in temperature. You must write this down. Increase, according to Le Chatelier's principle, an increase in what? In temperature. Favor endothermic. This is the first thing that you must write. Favor endothermic reaction. 1 mark for this. An increase in temperature favors endothermic reaction. Now, that is the first one. The second one, Where is this endothermic reaction here? Is it the forward or is it the reverse? We are guided by this. It's a forward reaction. So it means a forward reaction is favored. And guys, when we say something's being favored, means that side is the one which is increasing. So when we say a forward reaction is favored, it means the concentration of C and also D will increase, whereas B and A decrease, because we are favoring a forward. So what is the answer therefore? Therefore, the concentration of C will increase. This is the answer. So it means the answer for this one is increase. But if we said the temperature is decreased, then the answer will decrease because now if we're decreasing temperature, we're favoring exo, and exo will be reversed. It means this two, this one and this two is the one that will increase, C and D will decrease. So we're now favoring a reverse. I mean, in the context of it, they say, but you're controlled, you're guided by this. How about pressure? What they say about pressure according to Le Chatelier's principle? Number one, if you're increasing pressure, you favor the side that has fewer number of moles. So you're going to say, according to Le Chatelier's principle, an increase in pressure favor the reaction, favor the reaction with less or fewer number of moles, fewer number of moles. So when you increase pressure, ladies and gentlemen, the system will favor the reaction that has less number of moles. But by the way, on gases, not just anywhere, but only on gases. Right? Which reaction here? It is in gases. We only consider the ones that are in gases, not any other. Okay, this one is not in gases. We're not going to talk about that. This one is also not in gas. We're not going to talk about. We only consider the substances that are in gas, ladies and gentlemen. Right. Let's look on the left-hand side of the reaction. The reactants. It is the gas. How many moles are here? It's only 2 moles. This side is also a gas. How many moles? It's 3 moles. Which side have less number of moles is this one. So it means we are going to favor a reverse. So we'll say a reverse reaction is favored. A reverse reaction is favored. Obvious, if a reverse reaction is favored, means concentration of the reactants will increase and of the product will decrease. So it means the answer for number C is decrease. Because for C to increase, it means we need to decrease pressure. If we increase pressure, then the system will favor the side that has more number of moles. Then C will end up increasing. It's very important, ladies and gentlemen, to understand this. Then how about number 3? Addition of a catalyst increases both the forward and the reverse. It does not affect chemical equilibrium, so it means the answer here remains the same. It will have no effect on C because it increases both the forward and the reverse. So there will be no effect there. Okay, so the answer remains the same. Now, how about the last one? So number 4. Concentration of A is increased, or we have added more of A. I think I said this earlier. I'll just say this. Adding more of the A will use more of the B. And using more of the B As a result, concentration of B will ultimately decrease. Also with B will decrease. Then it will form more of the product, means concentration of C will increase and D will increase. That means the answer here is increase. You need to know we are talking about C. And a forward reaction is favored. I believe, ladies and gentlemen, you are following. Okay? Let's now continue. These are exam typical questions. Remember, practice makes perfect. All right, then now, don't forget to like, subscribe, ladies and gentlemen. Right. Let's now continue with our lesson, ladies and gentlemen. I believe you're following, okay. Okay, right. So we went through Le Chatelier's principle, explain the factors. Now we're gonna talk about on how to calculate the Kc. I strongly believe most of you know how to calculate Kc. We know Kc is the ratio of concentration of products over the concentration of reactants. But this one is for a forward direction, the Kc for a forward. So when you're calculating Kc for a forward, usually when you say calculate Kc, we're generally referring to a forward. So it means this is the concentration of products over concentration of reactants. But in the exam, if they say calculate Kc, you must know that you are calculating Kc for a forward all the time. And bear in mind, when we are calculating Kc, we do not include solids and liquids in our workings. Why? Because the solids and liquid, its concentration are assumed to be constant. So they are excluded. Okay, guys, I apologize. I just had connection issues. As I was saying that when we are calculating Kc, particularly for a forward direction, Kc is calculated by using the concentration of the products over the concentration of the reactants. But however, this one is for a forward reaction, which means if they say calculate the Kc for a reverse, this is the same as we just say 1 over Kc for a forward direction. But usually in the exam, if they say calculate Kc, always it's for a forward direction. So if they say for a reverse, then you just say, you just do the reciprocal. Now, I want to do one question that is involving Kc calculations. And again, there is one thing that I also want to add before I do one question. You must also know that when the only factor that can within like from temperature, concentration, and pressure. Remember, these are the factors that are affecting chemical equilibrium. But within this, there is one factor that is actually can affect Kc. Kc can be changed by changing the temperature. So it means temperature is one of the factors that can affect Kc, not concentration and not pressure. So Kc is only affected by temperature. Increasing or decreasing temperature will affect Kc. It's very important. Very, very, very important. And one other thing you need to be able to know is that, for example, if Kc is bigger than 1, it means that there are more products than reactants. But when the Kc it's less than 1, it means there are more reactants than products. But you must know that if you want to increase Kc, you can affect Kc by only affecting the temperature. For example, let's say you have this hypothetical reaction. Let's say it says 2 moles of A, it's an aqua, plus 3 moles of B, it's a gas, just an example. Okay, let's say it's an aqua. Then the reaction is reversible, then it gives us AB as an aqua. Obviously, remember I said when you're calculating Kc, we do not use solids and so it means these are the reactants. So these are the product. For a forward reaction, it means the Kc would be concentration of AB, because each coefficient is 1, we're not going to put anything here, divide by the concentration of A squared times the concentration of B squared. Now let's just say the reaction here, there is an energy that is being added here on the in the products. Let me just remove this, put it there. So once we're given this, we already know that, okay, it means an energy is being added in the product. So it means this is an example of an endothermic reaction because product absorbed energy. So which means the forward will be the endo, and the reverse would be the exo. So in the exam, if they say, what will happen to the Kc if we decrease temperature? Then obviously you're going to have to state this using the Talia's principle to say a decrease in temperature will always favor exothermic reaction. Then from our reaction here, which one is the exo? Is it the forward or is it the reverse? Obviously it's the reverse. It means a reverse reaction is favored. If a reverse reaction is favored, it means concentration of both A and B will increase, whereas the AB will decrease. So let's go to our formula. We said concentration of AB has decreased, whereas concentration of the A and the B will increase. We know in terms of mathematical, we know that anything that is in the denominator is an inverse relationship. So which means if there's an increase in the product, it means this has to decrease. Or other way around. The product are less, so it means the decrease means these are directly proportional. Another way would be to say, this time around we have more reactants. But in yes, more reactants than the product, which means the case would be less than 1. So obviously it shows that the value is decreasing. Now, yeah, but in the context of what I'm just saying, that is Kc is concentration of products over the reactants. Products are more, reactants are less. So if you compare this, there's a direct, so it means if this decreases, this one has to decrease. Or if this one increases, this one has to increase. To decrease, I'm to say they're inversely proportional. So it means the answer for this one, it will be the Kc will actually decrease. So it's very important to understand that. So now, ladies and gentlemen, I want to take you through the Kc calculation. I will just look on one hypothetical equation on how to actually calculate Kc. Okay, let me just share one question. Okay. Yeah, here is the question, guys. Let me just try to zoom it a bit. Okay, it says the equation below represents a hypothetical reaction that reaches equilibrium in the container after 2 minutes, somewhere here from the graph. And sometimes if you want to check where the graph, where the reaction has reached equilibrium, you'll see by the graph not increasing and decreasing, they're just constant. So it shows that between 2 minutes. Okay, fine. Let me just read the statement first, and we'll come back to this. Okay, then we are also told that it reaches equilibrium in a closed container after 2 minutes at the room temperature. Letters X, Y, and Z. Letter X, Y, and Z represent the number of moles of the balance. So we're just given a hypothetical reaction with unknown number of moles. So we have the A, and this is an aqua, plus we have the B, this also an aqua, and the reaction is reversible. Then this becomes C into an aqueous. So in terms of the moles, this one has X mole, and this one has Y mole, and this one has Z mole. So it means these are the mole ratio actually. And we know very well that when we're going to calculate Kc, we have to use them. Right, the graph below shows the change in number of mole of reactants and product versus time during the reaction. Now let's now analyze the diagram. Within this, on the y-axis, this number of reactants or product in moles. So this is the number of mole. The y-axis is the time in minutes. So it's very important to be able to understand your like the graphs in terms of interpretation of the graphs. If we look at this, it shows that this graph, this one is for A. The A started with an initial moles of 16, if I'm not mistaken. At time 0, A had an initial moles of 16. Whereas B had an initial mole of 8. And by that time, the initial mole of C was 0, because this is just the product. So you need to be able to understand the graphs. So within this, so this at time 0, the initial mole of C is the product, by the way. It's 0, whereas the reactants A and B start with an initial mole of 8 and 12. But after some time, after 2 minutes, between 2 minutes and 4 minutes, this shows that the direction was in equilibrium state. The forward and the reverse are now equal. So now, but after 4 minutes, there was a disturbance along the way, which resulted to A being increased in terms of the number of mole, and also with B also increased in terms, then C decreased. But a new equilibrium was established after at 6 seconds actually. After 6 seconds, or yes, after 6 seconds, a new equilibrium was re-established. There's something which you need to understand here is that if we were to calculate Kc, whether there's a disturbance here and here, the Kc should be the same. But we'll talk about that. So it means within between 6 and 8, still there's a new equilibrium after the disturbances. Now, we need to do it like this. I just want us to analyze this question without having to look at the question, but let's just analyze this. First of all, if we were to actually understand this deep, we're going to say, okay, fine. To analyze this, let's just use what you call a mice table. To say we have a mole ratio. Under mole ratio, then we have the initial in mole. We have the change of the reactant. In other words, they call it reactant, also in mole. Then the last one, it is equilibrium, also in mole. So this one is called the mice table. And within this, we're going to have the following. We have 3 substances here. I'll put them as they are. I just want us to analyze this, ladies and gentlemen. So we call this a mice table. Right, the final result here, we want to calculate the concentration at equilibrium, which means the Kc, you only use this concentration that are at equilibrium. So we know concentration is number of mole over volume. So if this at equilibrium, we knew this was the concentration, then there was no need, we're just gonna calculate Kc. We do the substitution because this is the concentration. It's if we had concentration at equilibrium. But however, this is not concentration at equilibrium, it is the number of moles at equilibrium. So I'm gonna do this, ladies and gents. Okay, fine. This is the A, the reactants. Oh, I apologize. This is the A, this is the B, and this is the C. Right, the mole ratio here, the mole ratio for substance A, it's X. The mole ratio for Y, for B, it's Y. And for mole ratio of C, it's Z. Right, now, ladies and gentlemen, I just want to analyze this. I don't want to go through the questions. I just want us to analyze this first. Now, we know very well that this initial, it is the information about the reactants and the product during the start of the reaction. When we look from the graph at time 0, initially, substance A came with 16 moles as its initial number of moles. So the initial number of moles of A, it's 16 here. It means initially A had how many moles? 16 moles. Whereas B had how many moles? 8 moles. And at that time, the initial number of moles of Z is 0. Usually, in most of the cases you see in the reactant, in the product, they usually put 0 there or a dash. To show that when the reactants are taking place, product by that time are not there. But when times proceed, then the product are now formed. Now, let us go and look at what has happened. Initially, A started with 16 mole, but it reached equilibrium with a mole of 8. So it means at equilibrium here, A remained with 8 moles, if I'm not mistaken. Whereas B started with 8 mole, but it reaches equilibrium here with 4 moles. Whereas C started with 0 moles, but at equilibrium, it had 12 moles. And you need to understand something, ladies and gentlemen. Sometimes in the marking guideline, they will not tell you this. You can easily see that the reactants, when they react, they get used up. Its moles decreases. That's why under change, the part for change for A and B, usually we put a minus, but they don't show this. Whereas the C has increased, which means there's a plus here. But sometimes they don't show it in the memorandum. So you need to make sure that the reactants get used up. So it means from initial they change and they form like they remain at equilibrium. So which means that initially the substance has 16 moles, then after some time the A decreased in terms of mole, then now it is at equilibrium. And how can we get these values, ladies and gentlemen? Usually when you are dealing with a mice table, if you get any value under change, you can be able to get all the values. But now here, ladies and gentlemen, we do not have the mole ratio. So to do this, we'll say, okay, fine. Initially 8, let me say A started with 16 moles, then it reaches the equilibrium with 8 moles. So the question is, it decreased by how many moles? Okay, just a minute, guys. Okay, okay, I apologize, guys. Right, as I was saying that, look, A actually started with 16 more, but it changed or it reacted. So it means we need to know what is the number of moles that is reacted, because now it's remained with 18 moles, 8 moles, which means it shows that it has decreased by 8 moles. So it means, that's what I'm saying, there's a minus here. So we need to put 8 here. To say 16 minus 8, this gives us 8. So, but sometimes in the marking guideline, they don't put this minus here. So it shows that under the reactants, we usually decrease because the reactants get used up and the product are formed. But in the product, initially started with 0 moles for Z, but now the Z now increased by how much? Obviously, it will be 12. So let's ask ourselves, where the answer will be 4. I believe you are following. I believe you guys are following. Okay? Then now, this one, this side, what is the value now? The value, this becomes 12. Why? Because 0 plus 12, it gives 12. So you can easily see that we can still get the number of concentration if we know the volume here. Remember, we use concentration at equilibrium, but now ever we do not know what is the X here, what is the Y, and what was the Z. Okay? Now, if we actually wanted to know what is the value of X, and what is the value of Y, and what is the value of X? I'm saying Z, straightforward. We can do this, we can say, okay, fine. Usually we do this. Will we consider the change values? The change values are the one that will give us a ratio. The reacted one, it shows that we have 8, 4, and 12. Let's do this. Let's now write this to its simplest form. By so doing, you realize that the number that goes into 8, 4, and 12 is 4. So which means we can divide by 4 throughout. Let's divide here by 4, by 4, 4. This one means it will be 2, 1, 3. Then it means now, if we do this, I want to show you something very important. If we put these values here as, okay, 2, this is 2, 1, and 3. We need to confirm that those are the correct answers. Remember, according to this, it says in order to deal with this, if you know any value under change, let's assume we do not know. If you know any value under change, then you create a scale. You do this. You take, this is a scale. You take your change value, you divide by the mole ratio, and it's a multiply by the next mole ratio. So it's, in other words, it's change over mole ratio. So let's assume we do not know this value. We just go, that's what I'm saying. If you get one value for change, then it will be easier to get the others. Okay, let's say we do not know the A and the B. So to do this, we're gonna say, okay, fine. The change, we just get any value under change. Do we have any value under changes for CS? So we're gonna say, do we have any value under change? Yes, it's there, it's 12. Okay, let me just use a different one. So if we just have one value under change, it will be easier for us to get the answer. So it will be change over, what is its mole ratio? Its mole ratio, it's 3. So it's change over the mole ratio. We make a scale. Change over the mole ratio. Do we have any value under change? Yes, it's 12 over 3 times. 12 over 3, it's 4 times. If we want to get this value this side, we multiply the mole by the mole ratio of that value. So you see the mole ratio, it's 1. So we're going to multiply here by 1. 4 times 1, this gives us 4. Same applies if we want to get this one for the A. What do we do? Already create the scale, then we multiply it by the mole ratio. What is the mole ratio here? The mole ratio is 2. So we multiply by 2. So this one gives us 8. So, and we have seen that we got this initial. 16 minus 8, it's 8. 8 minus 4, it's 4. Then those are the answers. So now, in the question, if I'm not mistaken, I do not want to get rid of these things. Okay, let's just go up and try to look at this. So the first question says, define a dynamic equilibrium. I think that one is straightforward. I'm not gonna do it, ladies and gentlemen. And the other one, actually, then the next question says, use the information in the graph and write down the values of X, Y, and Z. By the way, we have our mole ratio, which means we have the values now. The X, it's 2. The Y, it's 1. And the Z, it's 3. Okay, then now, the second question says, calculate the equilibrium or the constant, which is the Kc for this hypothetical reaction at the room temperature if the volume of the closed is 3. We are given a volume. Honestly speaking, when we are just given a graph like this, ladies and gentlemen, there is no need to use the mice table. I was just using it so that we can be able to understand the values of X and Y. Why? Because already they gave us the information at equilibrium. They gave us the number of moles at equilibrium, which means once we know the information at equilibrium, then it's easier to calculate because we are given the number of moles at equilibrium. And when we are calculating Kc, we use the equation information that is at equilibrium. So it means to do this, the only relevant information was just this, the 8, the 14, and the 12, which was at equilibrium. But since it's the mole, we want it as the concentration. What is the volume here? 3. So it's going to be number of mole over volume. So this will be 8 over 3, 4 over 3, and 12 over 3. Then this will be the concentration in moles per decimeter cubic. So 8 over 3, it's 2.67. 2.67 moles per decimeter cubic. Then 4 over 3, it's 1.33. Then 12 over 3, it's 4. These are the concentrations. So now we can now calculate the Kc. By the way, ladies and gentlemen, we now know the values of X2, 1 and 3. So it means we're going to say Kc. Let's check. We do not have gas, I'm say solid and liquids. Okay, fine. It will be the concentration of the C squared, I'm saying cubic, goes to the power of 3 here. C cubic, because our Z is 3. So it will be cubic over concentration of A. The mole is 2 times concentration of B, the mole is 1. So let's do the calculation. C, concentration of C is 12 to the power of 3. Concentration of A is 2.67 squared. B is 1.33. So let's do the working. 4 cubic over 2.67 squared by 1.33. This will give us 6.95. I'm saying 6.75 if I'm not mistaken. 2.67 is the A squared, 1.33 is the B. Then the C, it's 4 cubic, which is just 6. Then mark that. Now, this is the Kc for a forward. And in the exam, if they can say calculate the Kc for a reverse, then they say 1 mark. It's straightforward. We just say 1 divided by this, which is 6.75. So 1 divided by 6.75, that is the Kc. So it will be 0.15. I mean, if they say calculate the Kc for a reverse, but there's no need. Okay, then now the next question, 6.4, it says, at 4 minutes, they're referring to, at 4 minutes, the temperature of the system is increased. They increase the temperature. They've increased the temperature. And we know very well that when you increase temperature, you'll always favor endothermic reaction, according to Lutetius principle. So here the question says, is the reverse reaction exo or endothermic? We want to take decision whether, we want to tell whether the reverse is endo or exo. Explain how you arrived at the answer. Look at these guys. Let's just analyze this first. Looking at the graph, we are talking about A, B, and C. All are aqueous. Okay. There's no need for the talk. Okay, it's fine. Let me just put the moles. Look, they are saying after 4 minutes, the temperature was increased. They increased the temperature to 60 degrees. Let's check what happened after the temperature was increased. Let's check something here. You see that after 4 minutes, after they've increased the temperature, let's look on about A. You see that the information for A has increased. It means the number of mole has increased for A. And obviously, if the number of mole of A increased, means even its concentration will increase. A has increased. Let's now look at B. The B also increased. B has increased. Then now, look at the C. The C had decreased. C has decreased. And we know very well that, okay, fine. Look at this. This side has increased, this side has decreased. So what does it mean? It means a reverse reaction is favored. And since a reverse reaction is the one that is favored when we increase temperature, it means this side is where we have endo. Because remember, increasing the temperature always favors endothermic reaction. And since the endothermic reaction is favored, when there is an increase in concentration, it means that it's the side where the reaction is favored. By looking at this, you can easily see that both A and B had increased in terms of number of mole. So it means its concentration also increased. It means the reverse reaction is favored. And if the reverse reaction is favored, what does it mean? It means the reverse reaction is the one which is endothermic. Why am I saying this? Number one, they're saying we need to explain why are we saying that. So first of all, we're going to say, according to Le Chatelier's principle, an increase in temperature favor endothermic reaction. Number one, must write this all the time. Now, as a result here, look, the concentration of A and B increased. True. Whereas concentration of C decreased. And what does this mean? It means that a reverse reaction is favored. And since the reverse reaction is favored, means the reverse reaction is endothermic reaction, ladies and gentlemen. Remember, practice makes perfect. They can still bring this question, the mice table with unknown variable. You still apply the same. Remember the issue of minus in the examination, they don't put this, but you just have to know that. Okay? So it's very important, ladies and gentlemen, to understand this. Okay, let's now return to our. Okay, so already we went through chemical equilibrium, rate of reaction. Kindly watch the video for the rate of reaction, ladies and gentlemen. Went through a chemical change. Then now we are left with acid and base and the issue of electrochemical reaction. Electrochemical reaction. Okay, so what I will do now is I'll just address the part for electrochemical reaction, because acid and base is kind of like long, so I'll create its last part. Yeah, like we have part 3 of it, and maybe a bit of electrochemical reaction. Now, number one, let's start with electrochemical reaction. This is one of the easiest, ladies and gentlemen. Under chemical reaction, you need to be able to define what is reduction and what is oxidation in terms of electron transfer, Obvious, oxidation in terms of electron transfer is the loss of electrons. Whereas reduction is the gaining of electrons. So you need to be able to define this in terms of electron transfer, oxidation, and you can also think of what you call oil rig. Oil rig, which says oxidation is the loss, reduction is the gain. So it's very important to be able to define reduction and oxidation in terms of electron transfer. Again, you must be able to define oxidation and reduction in terms of oxidation number. And this is very important, which means oxidation is an increase in oxidation number. A substance that undergoes oxidation, you'll see it with an increase in oxidation number. And a substance that undergoes reduction, you will see by a decrease, is a decrease in oxidation number. If there is a decrease in oxidation number, you know this undergoes reduction. So when you are given a half reaction, you need to be able to know that the oxidation number, if there's an increase in oxidation number, you must know that reaction undergoes reduction. But if I'm saying increase in oxidation number undergo oxidation, then decrease undergoes reduction. So in the exam, if they say define the term oxidation, so it's either you say is the loss of electrons or you say it's an increase in oxidation number because they were not specific. And again, you must be able to define what are the cathode and the anode, very important. These are electrodes. Remember, an electrode is just a metal or a graphite that is used to conduct electricity. But now, here they want us to define what is the cathode and what is an anode. These are straightforward. These are electrodes. Cathode, it's an electrode. Anode, it's also an electrode. So a cathode is an electrode where reduction takes place, where there is a gain of electrons. It is an electrode where reduction takes place. Anode is an electrode where oxidation takes place. So you need to be able to know this, ladies and gentlemen. It's very important to be able to understand that. And again, you need to be able to define the term oxidizing or reducing agent in terms of electron transfer. We'll talk about this, ladies and gentlemen. This is one of the easiest chapter, actually. You need to make sure that you go through it so that you get a lot of marks from this one. So what is an oxidizing agent? This has to do with reduction. In another book, we call it the OA. Oxidizing agent is the substance that gains electrons. A substance that gains electrons. It's called an oxidizing agent. In another book, they say it is the substance that has the ability of gaining electron while itself is reduced. Whereas a reducing agent, which is the Ra, is a substance that lose electrons. So it means oxidizing agent has to do with reduction. Reducing agent has to do with oxidation. We'll talk about this. And ladies and gentlemen, ladies and gentlemen, another thing that is very important, let me just take you through the issue of oxidation number. When, let's say we have a half reaction of this form, guys, it's very important. I'm going to take you through grade 11 where you learn about oxidation number. Particularly in your syllabus, let me just say we write this. If I say, let's say it's just an example. If I just say silver as an ion plus an electron, then gives us silver as a solid. Then I'm going to change this reaction again. I want you to understand something very important here. Silver as a solid give rise to silver ion plus an electron. Very important, ladies and gentlemen. In grade 11, you went through a chapter called redox reaction, which has to do with oxidation number. An oxidation number, ladies and gentlemen, it's a number assigned. The number assigned to each element or an ion in a reaction or in a compound. The number that is assigned, if we assign a number to every element, that number is actually called an oxidation number. But specifically in your syllabus, guys, I want to talk about the rules of oxidation number, particularly in your syllabus. I'll just put ON. Number one, you must know something. The oxidation number of a pure element is 0. The oxidation number of any pure element is 0. And the oxidation number of an ion is equal to the ion charge. So what does this mean? It means if I say we have magnesium, magnesium is just an element, it's a solid. So since this is just an element, so it's a pure element, so its oxidation number always is 0. But if I write magnesium ion, this is now an ion, it's not an element. So the oxidation number of an ion, it's an ion charge itself, so it's just 2. For example, if I write chlorine as an ion, the oxidation number of this ion is an ion charge itself, it's -1. So once you know this, then it will be easier for you, ladies and gentlemen. Let's go back to the definition. Remember I said oxidation is an increase in oxidation number. A substance that undergoes oxidation, you'll see by an increase in oxidation number. But the one that undergoes reduction, you'll see by a decrease in oxidation number. Let's start with this. We have 2 reactions here for silver. If you look on the first one, this is an ion. Plus means there's a +1 charge here. So what is an oxidation number of this silver ion? It's 1, because I said the oxidation number of an ion, it's an ion itself. But this one, it's now a pure element because it's a solid pure element. And what is the oxidation number of a pure element? 0. Now let's check. The oxidation number moves from 0 to, I'm saying from 1 to 0. Are you saying the oxidation number is decreasing or increasing? The oxidation number is decreasing. So which means when there is a decrease in oxidation number, this reaction undergoes reduction. It shows that this silver ion has gained electrons to form silver. And I think I explained what is an oxidizing. I said oxidizing agent is the substance that gains electrons. So it means this is an example of the oxidizing agent. This one, it means it will lose electrons, so it will be a reducing agent. But we'll talk about that. So this half reaction undergoes reduction. But let's look at this side when we have changed this side. What is the oxidation number? It's now 0. Now this is an ion, so it's now 1. So it means it moves from 0 to 1. You see, there is an increase in oxidation number. So if there is an increase in it, means this reaction here, it's oxidation. So in the examination, when you are writing your half reaction, you need to consider the issue of increase and decrease of oxidation numbers. This is very important, ladies and gentlemen. Ladies and gentlemen, very, 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 very important, ladies and gentlemen. Then let's move on. Again, one must be able to know the two types of electrochemical cells, very important in your syllabus, galvanic cell and electrolytic cell. And you must also speak about the differences actually. The difference between the galvanic cell and electrolytic cell in terms of their structure or in terms of their functioning. It's very important, ladies and gentlemen. This is one of the topics that has a lot of marks. We need to make sure that you understand what you are doing. Okay? Now, let's now talk about the difference between electrolytic cell and galvanic cell. And we can also give examples of a galvanic cell. A car battery is an example of a galvanic cell. And what is the difference between the two? Okay, let me just summarize a bit about the two. It's very important to be able to know. So let's talk about galvanic cell. Galvanic, another name is called voltaic. In a galvanic cell, we usually use 12 cells. Where within these 12 cells, there's an inverted U-shaped tube, which is called a salt bridge. I apologize. Okay, let me try to increase this speaker of mine. So then within this, we have the electrodes, which are inserted in each of cell. The electrode, one of the electrode is positive and the other one is negative. And within this, there is a voltmeter around. So this is an example of a galvanic cell or a voltaic cell because of this. Now, there's something that you need to understand. Okay, let me just talk about this then. Again, we have an electrolytic cell. Under electrolytic cell, usually we use one cell. Within these two cells, we have the electrode. And within the electrode, then we connect a power supply. We'll talk about this. And inside this, then there's something called an electrolyte. Same applies here in this cell, there's also electrolytes. And this electrolyte, usually they are aqueous solution. Okay, then now look at these two things. Here, in an electrolytic cell, there is a power supply. There is a power supply here. And the electrode are in one half cell, in one cell. Unlike these, they are in separate cell and they are separated by a U-shaped tube. U-inverted shaped tube, which is called a salt bridge. And one must be able to know the function of a salt bridge, ladies and gentlemen. Now, the difference between the two is that number one, let me just talk about this. In a galvanic cell, we convert chemical energy to electrical energy. It means galvanic cell uses chemical to produce electricity, but this one uses electricity to produce chemical. So it converts electrical energy to chemical energy. It's very important. Secondly, in terms of structures, this one it's inserted into 12 cells, then this one is in one cell, but we're not going to talk about that. The reaction in a galvanic cell, it's called a spontaneous reaction. It means spontaneous reaction takes place in a galvanic cell. What does it mean by a spontaneous? It means it's a self-sustaining reaction, self-sustaining reaction. It's a reaction that takes place on itself, which means when we calculate the E cell, we'll be talking about this. The E cell for a galvanic cell, it's always positive, bigger than 0. But in an electrolytic cell, this is an example of a non-spontaneous reaction. Which means it's not a self-sustaining reaction. The E cell is negative. Why? It means, remember, it uses electricity. So it means without electricity, the reaction will not take place. Like right now, if you're experiencing the load shedding, then using this, it means the process will not take place. It's just an example. And under a galvanic cell, ladies and gentlemen, exothermic reaction takes place. Whereas this side, endothermic reaction occurs. An example of a galvanic cell, ladies and gentlemen, is a car battery. Remember, on a car, the battery does not need any electricity. It produces electricity on its own by using chemicals. So that's why we say it's a spontaneous reaction. But in terms of structure, I want to address something very important. In a galvanic cell, the negative terminal is the anode, and the positive terminal is the cathode. But this side, it's vice versa. The positive is the cathode, the anode, and the negative is the cathode. Why is this possible? It's because when we connected a power supply, the longer line we know on a battery, the longer line is the positive, this one is the negative. So if we have a plus and the minus, it means current will come this side. And if current comes this side, it means this will lose electrons. The electrode will lose, and if it starts to lose, it means it's the one that undergoes oxidation, which means it's the one which is the anode. Then this one will gain electrons, then it will be the cathode. So that's why in the galvanic cell, the negative is the anode, the positive is the cathode. And always, because this one loses electrons, it means the electrons will move from anode to cathode. This is the direction of the electrons. Why? Because if this one starts to lose electrons will flow and go through the cathode. It means this one will gain electrons. So it's very important to be able to know that. So you need to be able to know that the anode in the galvanic cell is the negative terminal, the cathode is the positive terminal. And always electrons move from anode to cathode. It's very important to be able to know the difference between galvanic cell and electrolytic cell. Another thing, galvanic cell has a salt bridge, whereas electrolytic cell has no salt bridge. And again, in a galvanic cell, the process of electrolysis does not take place. It means it takes place under the electrolytic cell. The process of electrolysis, sorry. Electrolysis is the process whereby electrical energy is converted to chemical energy. Actually, we can say it's the breaking down of molecules or ions by means of an electric current. So it means the process of electrolysis does not take place in the galvanic cell. And you need to be able to know what is an electrolyte. An electrolyte, it's a molten or ionic compound used to conduct electricity. And usually it's an aqueous solution. And again, ladies and gentlemen, you need to be able, okay, fine, let me just go through this. We defined what is a cathode, anode, oxidizing agent, reducing. Now I'm explaining the galvanic and electrolytic cell. I believe you're following. And again, you must be able to know the structure of a galvanic cell. Structure of a galvanic cell, I think I explained that galvanic cell has the electrode as the electrolyte in it, as the salt bridge. We need to talk about this. And also it has the voltmeter, just to measure the potential difference. Remember, galvanometer, it means it's a large voltmeter. Hence, they say galvanic cell. Then again, you need to be able to represent the galvanic cell in a cell notation. And this is very important, ladies and gentlemen. Let's talk about how to represent a galvanic cell using a cell notation. Right. When you want to represent a galvanic cell using a cell notation, you need to do the following. There is a principle that I was just using, or like a system that I was using to remember how to draw the cell notation, guys, which says, okay, cell notation. Remember, cell notation applies to a galvanic cell only. When they say to you, draw or write down the cell notation, this is what you should do. You should do this. Remember this. Andile cell coffee. Andile cell coffee. It's either coffee or chocolate. Andile cell coffee. Andile cell coffee. Andile cell coffee. Andile cell coffee. The cell here is for the salt bridge. Then this part of the lower side of the salt bridge, it means it's for the andile, and the right side is for the coffee. So what does this andile? Andile is for anode. Coffee is for the cathode. It means the left side is the information for the cathode electrode. And here, what you do, remember I said andile cell coffee. So within the andile, one side, listen to me very well, we need to always start with the electrode. Usually an electrode should be a solid. After electrode, then we come with to the electrolyte. The aqua. Same applies. Electrolyte and electrode. So it means the electrode should be at the end point all the time. Solids are electrodes. Electrolytes are aqua. And guys, you need to be able to understand this. This single line, the double line here, represents salt bridge. The single line is called a phase boundary. Or an interface. Phase boundary or interface. All the time, electrode, electrolyte, electrolyte, electrode. But andile cell coffee. Start with the anode part, then the cathode part. And the way you have written the electrode and the electrolyte, it must tell you that from the electrode to the electrolyte, the oxidation number must increase. But on the cathode, from the electrolyte to the electrode, the oxidation number must decrease. Very important. And this applies to a galvanic cell. Once they give you information like this, you must know you're dealing with a galvanic cell. Okay, then again, you need to be able to know the functions of a salt bridge. Very important in the galvanic cell. The function of the salt bridge is to, first of all, it maintain electrical neutrality. By separating the two half cells. And again, it completes the circuit. Complete the circuit, it maintains electrical neutrality between the two half cells. We can also say it separate the two half cells, but the two half cells by maintaining electrical neutrality. So these are the functions of the salt bridge. And inside this salt bridge, if we put an inert reactant, for example, sodium nitrate. Sodium nitrate has a cation and an anion. So it means the positive ion must flow to the positive compartment, then the negative, but yet we must usually have a cotton wool to allow the two half cells not to mix each other. And again, you need to be able to know the standard conditions needed when you are performing an electrochemical reaction. I'm saying chemical cell, and these are very important. Sometimes they'll tell you in the exam, what are the standard conditions that are needed when you are performing an electrochemical cell, whether galvanic or electrolytic. Number one, if you are dealing with electrolytes, which are aqueous solution, they must have a concentration of 1 mole per decimeter cubic. So electrolyte must have a concentration of 1 mole per decimeter cubic if the electrolyte, and also the temperature should be 25 degrees Celsius, or also in Kelvin. In Kelvin, it means we have to take the 25 degrees, we add by 273, we add by 25. I think this will be 298 Kelvin. So it means we say 25 degrees Celsius or 298 Kelvin. Then lastly, if you are dealing with pressure, the pressure should be of gases should be either 1 atmospheric pressure or 101.3 kilopascal. If you are dealing with pressure in the context of gas, so you need to know this standard condition. And again, you need to be able to write down the half reaction for reduction and for oxidation using a standard potential table. I think I've done one example to say, imagine if we say this magnesium 2 plus, it gains 2 electrons, for example, plus 2 electrons, then it gives this one. What is this now? You must be able to check, okay, it's an ion. Oxidation number of an ion is an ion charge itself. Okay, guys, I apologize, guys. Just I had connection issues. So as I was saying, that you need to be able to write down the half reactions using the reduction potential half table, but I think I will address that. And again, by identifying the oxidizing agent or reducing agent from the half reaction, for example, okay, here I've just said, when you are identifying oxidizing agent, wherever there is an oxidizing agent, guys, you'll see by the number of electrons. So this is a formula that you need to use to identify. Oxidizing agent plus the number of electrons should be reducing. So it means where there is an oxidizing agent, there should be number of electrons added on it. Okay, so I was still saying that if you are determining, if we want to identify the oxidizing agent in a reaction, for example, let's say we have this, we have the, like we know that oxidizing agent plus the number of electrons should always give us the reducing agent. So if I say magnesium, it's an ion, plus 2 electrons, then gives me magnesium. What kind of a reaction is this? First of all, look at the oxidation number. The oxidation number of magnesium is 2, it's an ion. This one is 0. Because remember I said pure element is 0, ion is an ion charge. So there's a decrease in oxidation number. It means this thing undergoes a reduction. Now, wherever there is a number of electrons, listen to me, where there is a number of electrons added to whatever that substance is our oxidizing agent. So it means in this reaction, oxidizing agent is the magnesium ion because it has the ability of gaining electrons. Then magnesium as a solid is the reducing agent. Very important. But there are cases where you find that we have two reactions. One is a stronger reducing agent than the other. So, but we'll talk about that. Again, you need to be able to write the net ionic reaction or overall for the redox. I think we'll talk about that. Again, you need to be able to calculate the cell potential. Very important. E cell is the E cathode minus the E anode. Let's say you forgot about definition of reduction. In the formulation, they also write it as reduction minus oxidation. And again, they say E oxidizing agent. This is another guideline to say, oh, cathode is an electrode, but it's an electrode where reduction takes place. And reduction is the gain of electrons, which means a substance that gain electrons is the oxidizing agent. It's very important, guys. You need to know that. Again, you need to understand or to define the process of electrolysis. Electrolysis is the process whereby electrical energy, it's converted to chemical energy. You see, this takes place in an electrolytic cell. And you must know the application of electrolysis. First one, we have electroplating. Second one, it's called electrorefining. And the other one is the decomposition of copper. This is the application of electrolytic cell. And we know that when you talk about electroplating, this is the process of coating one metal. The process of coating one metal with another. So when we coat one metal with another, this is called electroplating. And what could be the possible reasons of coating? Might be to protect the metal from rust, or to give the metal a shiny appearance. So this could be the reason for electroplating. So this could be the possible reason of electroplating. So it's very important for you to be able to know this. And how does electroplating works? Let me just give you one example here. Let's say maybe you want to electroplate a spoon with a silver layer. There's a spoon. Then here we put a silver. It's just silver Ag. It's a solid. Then we connect a power supply. But our power supply should be like this, negative and positive. So that, okay, inside there we must put something that has to do with silver. For example, we can use silver nitrate. Then what will happen is when electron, remember from a battery, plus and minus, this is a plus, it means electricity will flow through the silver. So it means silver will start losing electrons, and those electrons will flow through the electrolyte. Then after some time, then the spoon will change color and have that layer of silver. So it means you're going to write two reactions. Reaction of silver at the anode where it's losing. Why am I writing like this? Because oxidation number is from 0 to 1. It's increasing, so oxidation is losing. Then again, another one is for silver when it is gaining the electrons. So I think I'll do one example relating to this. Then another one is the issue of electro refining. Electro refining, actually, in other book, they call it, like, depends, the purification of copper. And also have the decomposition of copper. These are the three applications of electrolysis. So you need to make sure that you go through it on your own, ladies and gentlemen. If there is any question, you will reach out to me. Right. Another thing, okay, I just want to talk about the standard potential of cell. I think this one you are used to. You understand it, how it works. It will be easier for me to continue with it, okay? I wanted to address the issue of writing the net ionic or the overall reaction. So here we have the standard potential table. I believe it's visible. This standard potential table, I believe you know how to use it. The reason they are calling it a standard reduction, they call it a reduction. Why? It means the way they wrote this, they wrote it such that there's a decrease in oxidation number. So it's already a reduction. For example, if you see, we look at this, it's not that visible. It's not showing well. It's not showing well. Okay, let me just go down. It's not showing well. Okay, just for example, if you look at this says ion 3 plus, then gain 3 electrons, then gives us ion. And let me check its E volts. The E volts of ion with ion 3 plus, where is it? It's negative 0.88. So this is negative 0.88. Negative 0.8. Okay, sorry. This is the E volts. Let's choose another one. Let's say we use copper. Copper 2 plus as an aqua plus 2 electrons. We use one arrow, no, not two. So you see, both of them, we wrote them as a reduction. You see, decrease in oxidation number from 3 to 0, from 2 to 0. We wrote them as a reduction. However, I want us to talk about the E volts here. Copper with copper 2 plus. Let me check something here. I think it's 0.34. So now, if you look at this, the E volts of a half reaction can easily tell us that which one will be like will undergo reduction. Yes, the reduction of reaction is like this. But if you look at the E volt, this one is much higher than that, which means anti-galvanic, this one will undergo reduction. This one will undergo oxidation. Why? Because if we calculate the E cell, remember we said the E cell for a galvanic should always be bigger than 0. So if we calculate, this is going to be E cell, it's E cathode, or E reduction minus E oxidation. What is the reduction here? It's 0.34 minus into minus 0.08. So let's work out this. This will be 0.34 minus into so plus 0.08. So this will be 0.42. You see that the answer is positive. And since if the E cell is positive, it means we are dealing with a spontaneous reaction. And spontaneous reaction takes place in the what? In the galvanic cell. Now, look at this. Both of these are written as reduction, but we need to rewrite them correcting. Remember, this is remember where I said where there's a number of electrons, it means this is our oxidizing agent. Even this also is the oxidizing, because oxidizing agent plus the number of electron would be a reducing. So it means these two are the reducing agent. But within the two, you see that iron and copper are reducing agent. But I wanted to show you something. Because this one undergoes reduction, this one undergoes reduction, it means copper ion is a stronger oxidizing agent than iron 3+. So this means this one gains more electrons than that. And when you look at this, because this one undergoes oxidation, it means this one is a stronger reducing agent than copper. So it means iron is a stronger reducing agent than copper ion. I'm saying copper as a solid. Why? Because this one loses, again, we said reducing agent is a substance that loses electrons. So, but if we were to balance this, we're going to say, okay, fine, let's start with the reduction. Which one undergoes reduction here? Obviously, the one that undergoes reduction is the one with the highest E volt, is going to be copper. So we're going to say Cu. So we write it as a reduction because both are reduction. So we're going to say copper 2+ as an aqua plus 2 electrons, then gives rise to copper. Question 1. Now we have to write oxidation. Remember, the return as reduction, but to write as oxidation means we must have a decrease. We must start this side going there. So it means we must have this. This is what we're going to get. Ion give rise to ion 3+, aqua plus 3 electrons. Let's look at this. You see, I've changed it because if we are writing it like this, oxidation number, it moves from 3 to 0. Now we want it to move from 0 to 3. So you see, this is 0, there is 3. It means there's an increase in oxidation, which is oxidation. Okay, now we can now balance the electrons to have an overall equal reaction. Look at this. We have 2 electrons there, and then we have 3, and we need to balance them. To balance them, it means they must be both 6. And to do that means you can multiply the equation this by 3, by this one by 2, because 3 times 2 is 6, 2 times 3 is 6. So it means we'll have this. It will be copper, by 3. 3 copper ion plus 6 electrons give rise to 3 copper as a solid. Then secondly, we will do the same. It will be 2 an ion give rise to 2 ion plus 6 electrons. But since the electrons are balanced, then we're going to do this. Whatever is on the right of this, we just want write one arrow. Whatever is on the right, we combine it together. On the right, we combine. But we start with the electrode, which is a solid. So it's going to be 2 Fe, it's a solid, plus the ion electrolyte. Same applies inside electrolyte. Electrolyte is this one. So it will be 2 ion 3+ as an aqua plus 3 moles of copper. So this is an ionic reaction. That's why within this you can be able to write the cell notation. Andile cell coffee. The Andile cell coffee. Because remember, the one that undergoes a reduction is the one that will be at the cathode. Oxidation will be one at the anode. So we're going to say Andile cell coffee. Cell is a salt bridge. Andile is for the cathode. I'm saying anode, cathode. Well, we'll start with the electrode. Between the andile, which one is the anode? The oxidation. This is it's an electrode, electrolyte. So we're going to start with Fe as a solid. Then phase boundary and ion, it's an electrolyte. Then this side we come with this. The cathode reduction, we start with the electrolyte. It's a copper ion. give rise to phase boundary copper. And to see that we've done it correctly, on the side of an anode, when we look, oxidation number is 0. It's now moved to 3, which is fine. Oxidation number is 2, it moves to 0, which is fine. Increase in oxidation number, we know is oxidation. Decrease is reduction. So always electrode, electrolyte. But usually in the exam, sometimes they can say, let's put this, since we have an electrolyte, we can say this has a concentration of 1 mole per decimeter cubic. 1 mole per decimeter cubic, because it's an electrolyte. So this is how we do the net overall reaction. Always, when you are looking at your standard potential half reaction, okay, let me just do this. So when you are looking at your standard potential half reaction table, if you copy a reaction or you write a reaction from left, so from your standard potential, you write a reaction from left to right, just know that that's always a reduction. But if you start from left, from right to left, that's just know this is oxidation. For example, if you copy this reaction like this as F2 is a gas plus 2 electrons, 1 arrow, not 2, you write 1 arrow, 2 moles of an ion, it's an aqua. An ion is an aqua. You see, oxidation number of this, because this is just a compound, 0. That's -1. You see, we're moving from 0 to -1. You see that there's a decrease in oxidation, that's why it becomes a reduction. But if you start this side, going this side will be an oxidation. So don't forget that, ladies and gentlemen. I think I'll also do one example. Maybe we're going through the like answering a question paper where we are going to address everything here. Yes. I think this is the end of the session, ladies and gentlemen. So I'll be left with acid and base part. I'll address the acid and base part in the next video session. I think that will be part 3, ladies and gentlemen. Yeah. Okay. Thank you. Thank you very much. Take care. Bye-bye.